Okay, so today what we're going to look at is exponential and logistic growth. And you looked at exponential growth in AB last year. Logistic growth is new for BC, but I think you've looked at both of them if you were in AP Bio. I'm pretty sure that's the science where it comes up. So some of this may look familiar. I think they call logistic growth S-curves, I think is what AP Bio calls them. But anyway, okay, starting out with exponential growth and decay. The function or the statement, I guess, that you need to know and recognize as exponential growth is that y changes at a rate that is proportional to, really need to call that y. So this quantity right here is the same as this quantity right here. What that turns into is the differential equation dy dt equals ky. Again, notice that the variable here in the numerator of the fraction matches the variable right here. Okay, so that's how we know that we have a differential equation that is exponential growth. We solve that differential equation and we get y is equal to ce to the kt. Now, we get to bypass all of the calculus when doing these problems. And we're going to do the calculus so that I can show you where it comes from, but then we get to bypass the calculus altogether. So in terms of what these things are, c is the initial value of y, so that's the initial value, and then k is what we call our constant of proportionality. It's going to be it's going to be a constant that differs depending on the conditions that our situation has. And we know that if k is positive, then we have exponential growth. If k is negative, then we have exponential decay. So the first thing that we're going to do is solve the equation dy dt equals ky. So I am going to set that over 1. And so that would be 1 dy is equal to ky times dt. Now I need to separate, remember, so I'm going to have to move my y over. So 1 over y dy is equal to k dt. I'm going to integrate both sides. Separate, separate, integrate, integrate. So on the left, here I get natural log absolute value of y. On the right, because of the dt, our t is our variable. So this would be like a 3. So the antiderivative of 3 would be 3t. So the antiderivative of k would be kt plus your constant c. Now I need to solve for y. So I am going to e both sides. So I would have the absolute value of y is equal to e to the kt plus c. And then I would remove my absolute values by putting a plus or minus over there in front of the e. Now that kind of looks like that, but it's not quite there. So how do we get from here to something that looks like that? Well, I'm going to take my equation, y is equal to plus minus e to the kt plus c, and I'm going to work with it algebraically. So the first thing that I'm going to do is I am going to give each of the exponents their own base. So they're each going to be raised to e is going to be raised to each exponent individually. And then remember, we multiply our bases together. Now, e to the c, this is all numbers. So because it's a big number, we can call it a big C. We don't know what it is, but it's just a number. It doesn't involve a variable. And then we can move and manipulate and put our C in front. So hence how we get y is equal to plus minus ce to the kt. All right, this is the calculus behind a differential exponential growth. We never have to do that again. If you can recognize this as an exponential growth problem, then you can go straight to the solution equation and be done with it. So let's look at an example. What are you going to be asked to do? Most of the time, what you're going to be asked to do is solving for c, for k, for values of y. So if we look at example 2, it says the rate of change of y is directly proportional to y. So if I were to write that as a differential equation, the rate of change of y would be dy dt, directly proportional to, that's k times, and it's directly proportional to y. So we should say, I know dy dt equals ky. I know that solves to y equals c e to the kt. I've done my calculus step. Now I'm ready to go back into algebra and plug in. So what do I know about this situation? I know that when t is equal to 0, y is equal to 3. So remember, c is our initial condition when t is equal to 0. So that gives me the equation y is equal to 3e to the kt. I also know that when t is equal to 2, y is equal to 6. So that gives me the 0.26. And if I plug in for x and t, I can solve for k. So if I divide by 2, I get 2 is equal to e to the 2k. If I natural log both sides, I get natural log of 2 is equal to 2k. So I end up with 1/2 natural log of 2 is equal to k. So now I have all missing pieces of my equation. So my equation is y equals 3e to the 1/2 natural log of 2 times t. And now that I know that, I can take my, let's see, I'm running out of colors. I can take my, what is the value of y when t equals 3, and I can plug it in. So when t is equal to 3, I get 3e to the 1/2 natural log of 2 times 3. And then that would be a calculator version. So 3e 0.5 natural log of 2 times 3 gives me that y would be equal to 8.4852. I think I pulled that right. 4852, yeah. So that would be our answer. Okay, so really there's no calculus involved. All right, we skip all the calculus. All right, for number 3, it says the number of bacteria in a culture is growing at a rate of p equals 3,000 e to the 2t over 5 per unit of time. At time t equals 0, the number of bacteria present was 75,000. Find the number present at t equals 5. Okay, so if we're growing at a rate of, okay, so this one's a little bit different because we're growing at a rate of p. So that's really a derivative. So if we want to find the, we want to find the integral of p of t dt, then we would do the integral of 3,000 e to the 2t over 5 dt. Let's see, we would pull our reciprocal in front, so that would be 5/2 times 3,000 e to the 2t over 5, which would be, let's see, that would be 1,500. 5 times 15 would be 7,500 e to the 2t over 5. So that would be our equation, which matches at t equals 0, the number of bacteria present was 7,500. Find the number present at t equals 5. So now we want to do y of 5, which would be 7,500 e to the 2 times 5 over 5, which would be 7,500 e squared, which would be 7,500, oops, not that, clear that, 7,500 e squared would be 55,417.9207. Okay, so that time it was a little bit different. They gave us the differential equation, but it's already in that form, so we had to integrate it to come up with our original one. It wasn't in the dy dt equals ky form. All right, for example 4, A slow economy caused a company's annual revenue to drop from $530,000 in 2008 to $386 in 2010. If the revenue is following an exponential pattern of decline, what is the expected revenue in 2013? Okay, so what I'm going to do is I'm going to set my t equals 0 to correspond with 2008. So that means my initial condition is 530,000. So if t is equal to 2, that would be 2010. Okay, so that would be my revenue in 386,000. If we have an exponential pattern of decline, then we know our equation is y equals c e to the kt. And we know, or we're going to make our c value 530,000. So y is equal to 530,000 e to the kt. Now our job is to find k, and we're going to use our next piece of information. So we were told that at t equals 2, our revenue dropped to 386,000. So that would be 386,000 e to the 2k. No, 386,000. I am not on my game tonight. 386,000 is equal to 530,000 e to the 2k. There we go. Okay, so my calculator, I'm going to do my calculator work. So 386,123 divided by 530,123 is equal to 0.7283 is equal to e to the 2k. So now I need to natural log that guy. And I get negative 0.3170 is equal to 2k. So I can divide by 2, and I can get k is equal to negative 0.15851. Now I am going to store that into A because I really need to use that entire thing. Okay, now notice that k is negative because remember we said when k was negative, we have an exponential decay, a decay in the problem. All right, so we want to know what is going to be our revenue in 2013. So that would be when t is equal to, what, 5? So we are going to do y equals 530,000 e. So we've got our k value, negative 0.15851 times 5. And that's going to be our revenue. So let's see what we get when we do that. 530, 1, 2, 3. Second E. I'm going to do A times 5. And I get 239,913.37. Since we're talking about revenue, that's money, we should have 2 decimal places. All right, again, no calculus involved. All right, number 5, suppose that a colony of insects increases according to the exponential growth. There were 130 insects after the 3rd day of the experiment and 380 after the 7th day. Approximate how many insects were in the initial population. So we know it's according to the law of exponential growth. So we know y is equal to c e to the kt. The problem is this time they didn't give us c. They gave us 2 sets of data. So we know on the 3rd day there were 130 insects. So that would be this situation. So if I plug into my equation, I would have 130 is equal to c e to the 3k. On the 7th day, there were 380. So that would be 7,380. So that would be 380 is equal to c e to the 7k. So now we have a system to solve. And there's a lot of different ways that you can do this. I think let's see, I'm going to take the smaller of the powers, the exponents, and I'm going to solve for c. So I'm going to say that c is equal to 130 over e to the 3k. Then I'm going to take that c value and plug it in over here. So that would give me 380 is equal to 130 over e to the 3k times e to the 7k. So now I can reduce my e's, and so I get 380 is equal to 130 times e to the 4k, because 7k minus 3k is 4k. So now I can solve for k. So I've got 380 divided by 130 gives me 2.923 is equal to e to the 4k. So now I need to natural log that guy. So I get 1.0726 is equal to 4k, and now I need to divide by 4, and I get that k is equal to 0.26815. Now, I don't need that. What I want is the initial population, so I really want c. So c is going to be 130 over e to the 3 times that 0.26815, which is going to be, let's see, 130, actually I'm going to make it a fraction. 130 over e to the 3 times, and I'm going to go grab this value up here. Nope, I didn't mean to do that. I may not be able to grab that, so I'll have to multiply it by, I'll have to type it all in. 2, 6, 8, 1, 5, 9, 2, 0, 0, 6. Okay, there we go. So C is equal to 58.1518. So that is our initial condition. Okay. All right, so that's exponential growth. You do a lot more problems with exponential growth, or you do a lot more arithmetic and math with exponential growth than you do with logistic. So let's look at logistic. A logistic growth is where your y changes at a rate that is proportional to both the amount present and the difference between some limiting factor and the amount present. So here is your differential equation for this one. We have Kp times L minus P. Now it solves to be this guy, but you don't really need to know that. This is what you have to memorize. Okay, so here is a graph of a logistic curve. So see, I think you called them S-curves in biology. So if we look at this equation, if P is 0, if we plug 0 in for P, then dp dt is going to be 0. Now remember, dp dt is the slope. So if we look at as P goes to 0, P is on your y-axis, I mean your x-axis, no, yes, your y-axis, T is your x-axis. So as P goes to 0, can't you see our slope starting to go flat to 0? If P goes to L, L minus L would be 0, so 0 times anything would be 0, so our slope would be 0. So it looks like here's where our slope gets 0, so this right here would be our L value. Okay, where does the curve look like it's growing the fastest? Well, it looks like right around in here it's growing the fastest, which happens to be at, let's see, this is this is at a t equals 2. As t goes to infinity, what is P doing? So as t goes to infinity, P is going to whatever this L quantity is, which happens to be 4. The graph has a horizontal asymptote at y equals 4. Let's see, logistic curves have what is called a carrying capacity. So what do you think the carrying capacity of the solution above is? Well, it would happen to be 4, because that's as large as that graph can get. We can't get any more than 4. Where does the solution curve change concavity? It changes concavity right here at t equals 2. No. How about at P equals 2? That's your Y value. At Y value, P equals 2. Oh, this was P equals 2 as well. I kind of butchered this. All right, and then where do you think happens if the initial quantity is above the carrying capacity? So if we start above 4, then it's going to decrease instead of grow, okay? So let's put it all together. What are you going to have to know? All right, the population P of T of fish in a lake satisfies the logistic differential equation dP dt equals 3P minus P squared over 6,000, where T is measured in years. So the first thing that you've got to do is take your equation and write it as a logistic growth, which looks like this. Okay, so you have to write it in that form. So I need to factor out a P over 6,000. So I am going to have dP dt equals 1 over 6,000 P times, if I factor out a 1 over 6,000 P here, I end up with 3 times 6,000, which would be 18,000, minus, if I factor out a P over 6,000 here, I'm left with just a P. So now you can see, according to this question, that my K is equal to 1 over 6,000 and my L is equal to 18,000. So that's that according to the logistic growth model. Let me put this under there. Okay, so what do we need to know? If my initial condition is 4,000, then my limit at T, as T goes to infinity, is still going to be L. So that would be 18,000. That's as high as I can go. My inflection point is going to be at 1/2 of L. So that's going to be at P equals 9,000. Am I increasing or decreasing? Well, I'm starting at 4,000, increasing to 8,000, so I'm increasing. And my range is going to be from my starting point, 4,000, to my carrying capacity, 18,000. Now, starting point always has a bracket, carrying capacity always has a parenthesis, okay? If I change that initial quantity to 10,000, my carrying capacity, my limit, is still 18,000. It does not change. But this time, my point of inflection, it should happen at 9,000. Well, I started at 10,000, so this one is not going to have a point of inflection. It's going to be above its point of inflection. It is still going to be increasing, though, because we're starting at 10 and going up to 18, so it's still increasing. And its range is now going to be 10,000 to 18,000. Again, initial with a bracket, carrying capacity with a parenthesis. Right, if I start at 20,000, my carrying capacity is still 18,000. It will never change, guys. My point of inflection is still at 9,000. Well, I'm all the way up at 20, so there is not going to be a point of inflection. Because I start at 20, I'm going to have to decrease to get down to 18,000 because I can't sustain more than 18,000. And my range this time, I'm just going to flip them. It's going to be my 18,000, which is my carrying capacity, to my initial condition of 20,000. Because remember, it always goes big to small. So if I were to look at the graph, and I didn't draw it on here, but if I were to draw a graph for this guy, this would be my carrying capacity at 18,000. This would be my initial condition at 4,000, and my point of inflection would be here at 9,000. So it would look something like this. You would see the full S-curve. Here, if I have my carrying capacity at 18,000 still, but I have my starting point at 10,000, what you're going to get is just the top half of an S-curve. Okay, so you're not going to get the bottom concave up part. You're only going to get the concave down part. And if I start above my carrying capacity, let's say my carrying capacity is right here now at 18,000, but I'm starting up here at 20,000, I'm going to decrease down to 18,000. Okay? All right. So we don't do a whole lot with this other than answer the question, what is the carrying capacity? What is the limit as t goes to infinity? What is the inflection point? When is, okay, inflection point is also growing the fastest. Okay, so you need to know that. So they may ask for where is the graph growing the fastest. All right, so a new book hits the stands and becomes quite popular. The growth of readership in the book can be described by the differential equation dr dt equals 4r times 2 minus r over 200, where r represents the number of people having read the book in a particular office building and t is measured in days. Whew. Okay, first thing we have to do is factor out a 1 over 200 because we need this r to be r by itself. So if I pull out a 1 over 200, that turns my equation into dr dt is equal to 4 over 200 r times 400 minus r. Okay, we're going to multiply that 2 times that 200. All right, so what is the limit as t goes to infinity of r of t? Well, remember, this is your k, this is your L. The answer to that is L, so it would be 400. Find the value when of r when the readership is growing the fastest. Well, it's growing the fastest at half of L, so that would be at r equals 200. And that would be it. I mean, that's really what they ask you about, okay? All right, now sometimes they ask you to come up with a differential equation yourself. So it says the rate of change of the number of people in school who have heard a rumor is modeled by a logistic differential equation. So that means we know, let's just do dp over dt is equal to kp times L minus p. So that's our basics. It says there are 3,500 people in the school. So what do you think that represents? Okay, that represents L, our carrying capacity. So we know that L is 3,500. It says at 1 p.m., the number of people who have heard the rumor is 950. So that right there is going to represent P. That's the number of people who have heard the rumor, and is increasing at a rate of 250 people per hour. So that's going to be dp dt. So now we have all the information we need to be able to solve for k. So that's what our job is. So we are going to say, all right, so dp dt we said was 250 is equal to k times p was 950 times L we said was 3,500 minus P we said was 950. So let's see, what is 950 times 3,500 minus 950? So 250 is equal to 2422500 K. So now we can do 250 divided by that guy, and we get K is equal to 1.031 times 10 to the negative fourth. So now it says find the constant proportionality K. We did that, and write a differential equation to model this situation. So when we write our differential equation, we are going to plug in our value for L and our value for K. Everything else is left out as a variable. So our situation would be dp dt is equal to 1.031 times 10 to the negative 4p times, what did we say our L was? 3,500 minus p. That's a p. And that would be the differential equation to model that situation. Okay, so logistic growth is all about, I don't know if I did a great job, but logistic growth is all about memorizing the parts of the logistic growth equation. So you need to know, where is it? You need to know that as t goes to infinity, p goes to L, whatever the carrying capacity is. You need to know that it changes concavity at 1/2 of L. Okay, so you need to know that. You need to know that it is growing the fastest at 1/2 of L. So you need to know that. You need to know that it's got a horizontal asymptote at y equals L. You need to know that as p goes to 0, dp is 0, and as p goes to L, dp dt is 0. So you just need to know the characteristics of the graph and what's going on, okay? Because that's what they're going to ask you about. And then you've got to be able to know what the equation is so that you can factor it out and put it in the right form. All right, that is all for this unit. So if you have any questions, come see me. Thanks, guys. Bye-bye.